angular coordinates in n minus 1 dimension. N minus 1, not n minus 2. Why? Because when we are talking about the dimension, green function in Rn, so u is one variable, that is the dependent variable, and r, that is the radius of the polar coordinate, that is the distance from the origin of the circle, or distance of the boundary from the origin of the ball r, and the raised n minus 2 is going to be angular coordinates. So this is 1, and the rest is n minus 2. So basically we have n dimension. So the Laplacian in polar coordinates r comma w is given by Laplacian of u equals to u r plus n minus 1 r u r plus 1 over r delta s u, where differential operator delta s acts only on the angular coordinates w. So just take a look at this one. If n equals to 2, so this will simply reduce to u r plus 2 over r u r plus 1 over r square u theta theta. We have already studied about the solution of this Laplacian in two-dimensional when the boundary condition is given on r comma theta. So theta we are not provided with the boundary condition on theta in two dimension, because we know that because of the periodicity of the circle we already have a boundary condition on theta. At every 2 pi interval it is going to repeat itself. So we only get the boundary condition on r equals to a. Denote by w n minus 1 the area of the unit sphere. This symbol is 1 in Rn. So W1 is 2 pi, W2 is 4 pi. Now define the function. If you guys remember in the last previous classes, I gave some question as a homework, not in your assignment, just to calculate those things and to solve. Did anyone go through that questions? No?
No.
How do you guys revise the topic? Because I think that if you're not solving the question simultaneously, like sometimes I give it in class, so how do you revise it? Do you read books or just let it on the time when the exams will be coming and then we will be going through the notes?
I read the notes, the handwritten notes.
Because sometimes when I am in the flow of these classes and you're solving that question, so I feel that sometimes it is going to stuck in your mind, oh, from where this concept is coming. So that's why I give some questions in the classes just to take a look at that question, so that the next time when you are coming in the class, you will have a lot of doubts related to theory, not just related to the examples or just not related to the problem. So that's why every time I ask you to solve some questions which I give you in the class, because in this way you are going to strengthen your topic as well. But let's So except for the origin. So basically when we are going to define the green function, the green function has a singularity. Most of the time it is going to have the singularity at the center of the circle. So define the function g naught x in Rn except for the origin in such a way that z naught of x is equals to 1 over n minus 2 w n minus 1 r to the power n minus 2 when n is greater than or equals to 3, and this green function is defined as minus 1 over 2 pi logarithmic of r n equals to 2 where r is equals to modulus of s. So basically how we define the center of how we define the circle, modulus of x minus x naught is equals to its radius. So x is varying. Since x naught is taken to be 0 because we are considering the center of the circle is 0. So because of that, mod of x equals to r is the equation for the circle. Is it clear? Now again I am giving you an exercise just to take a look. When you will calculate the Laplacian of this g naught, if you will take the Laplacian of g naught in Rn, then you are going to see that the Laplacian of g naught is 0. You have to exclude 0 from the domain because this green function is not defined on r equals to 0, that is the center of the circle, that is the origin, because we are taking r in the denominator of this term, and here it is not defined because we are taking logarithmic of r, and logarithmic of r is not defined at 0. Please solve this. Now let the domain D is contained in Rn via bounded domain with the origin in its interior and for the radius r greater than 0, small, consider the domain dr, that is d minus r is less than r. So if we are trying to understand how we are taking this domain, so just understand its geometry. Although I cannot plot it in n dimension, but still I will try. So suppose this is your domain B, and then we are taking, this is origin. I'm just taking 3 dimension because for more than 3 dimension it is not possible to project it on the notebook. So let D is contained in Rn via bounded domain with the origin in its interior. So the origin is coming inside the domain. Now consider a positive quantity r greater than 0, that is a small quantity, and then consider a ball with the maximum radius r, and then exclude that ball with the domain. So consider this ball and its radius is r, where r is strictly less than r. So exclude this ball from the domain D. So this is the domain. Again, since we are excluding a bounded region from a bounded domain, so the final domain is going to be bounded. So dr equals to d minus r is less than r. Now again this dr is boundary. Applying Green's second identity to Z0 and an arbitrary function u from D to R, we find since this equation is satisfying in whole the region, so it is also going to satisfying on any bounded domain of this region Rn minus 0. So we can say that G naught is harmonic in Rn minus 0. Is not it? If a function which is satisfying the Laplacian equality in a domain, so we say that that function is harmonic in the domain. Is it true? Are you guys sleeping?
Yes.
Sleeping?
Yeah. No. Are you guys? I thought you said. Are you guys thinking?
No, I asked, are you guys sleeping?
No.
Because you're not answering my question, so I thought you might.
Not even close.
So, anyone remember Green's second identity? I expect that no one is remembering about that, but still, if anyone remember. So, if this Z naught is an harmonic function and U is any arbitrary function that needs only to be continuous, and even some case it does not need to be continuous. So if Z naught is a harmonic function, then the Green's identity says that delta dr is the boundary of this domain. What will be the boundary of this domain according to this figure? Can anyone tell me? What will be the boundary of this domain according to the draw figure? Can anyone tell me?
The circumference.
And this outer boundary is also going to be boundary now, because we are subtracting this radius, this circle of radius r less than r from the whole boundary. Now there is a hole in a domain. So what will be the boundary? The interior boundary and the exterior boundary, is not it? Because this is so a boundary and this is also a boundary, so it has two boundaries. This boundary will be known as the interior boundary. So if you are considering, just keep in your mind, if you are considering a problem of Dirichlet problem on the circle of radius r, so for exterior Dirichlet problem the region will be this and still the boundary will be this. For the interior Dirichlet problem, if you are considering the interior Dirichlet problem for this, so again the boundary will be this, but the region where the function is defined, that will be coming inside of that. It is just an illusion how you visualize those things, because sometimes you are doing the calculation, so that is not enough. You need to visualize at least in 3 dimensions you can. So since we are taking the integration over the boundary, so because of that this is the surface, small surface term, and this is equals to minus dr, the domain dr, z naught del u d of v. V is the volume. Since the second derivative of z naught in this domain is going to be 0, so because of that the second term will vanish. So this is the green second identity. You can turn over pages and can go over the green's first, second and third identity with the special case. Now since del dr is the union of the boundary del d and the boundary of uh, here I have written in the notes that boundary of the sphere. So I would like to point out that if we are in two dimension, then it will be a circle, it will be a disk. If we are in three dimension, then it will be a sphere. If we are in more than three dimension, then what you call it? What you will call it? Hmm? If you are in more than
Hypersphere.
no hypersphere, or you cannot say that it is a ball. Basically, like in your topological sentence, we call a ball linear dimension. Is not it?
Yes.
So this is just a way to write each and every term when you are writing. So it has a special meaning, and you need to understand what is the meaning of those terms. So the boundary of a sphere, circle, or ball. It is up to you which dimension you are considering. SR is equals to surface. So this is the boundary of that ball. We may also write as now this del dr is basically union of del d and del br. So it can be written as del d. It is the union, so the union can be break and it can be written as the summation. This is basically SR we're writing. If we multiply it with the negative sign and then we write minus, minus and then plus and then write it like now our next goal is to take the limit as r is approaching to 0, the limit when this radius is approaching to 0. So what happens? So consider first the integral over r sr and Now our next goal is to take limits as r is tending to 0. Consider first the integral over SR and recall dA is equals to r to the power n minus 1 dw in polar coordinates. On SR, also on SR we have if n is greater than or equals to 3, G naught is equals to 1 over n minus 1 W n minus 1 r to the power n minus 2 and del r G naught is equals to minus 1 over W n minus 1 r n minus 1. Thus the integral over SR equals you don't need to put a closed integral sign because if we are calculating the integral or this is fair, then we automatically know that this is a closed integral. dw. Now from where it is taking the gradient of u is bounded. U is an arbitrary function and we are taking it from D to R where D is a bounded region. If D and then S is contained in S, U is an arbitrary continuous function defined on a closed bounded domain is bounded. Okay. So since the gradient modulus value of the gradient of U is bounded in D, the limit of this term as r tends to 0 is minus n minus 2 u of 0. Now consider the integral over dr. Here we are using a lot of calculus with the application of the real analysis. I am not going to explain all the terms. You can go over the integral of a green function and then you will find each and everything. Now consider the integral over dr, which is the difference of the integrals of z naught Laplacian of u over d and over the ball b of r. So this written in the polar coordinates as 1 over w n minus 1 0 to capital R s 1 over r to the power n minus 2 Laplacian of u r w r to the power n minus 1 dw over dr. in absolute
Descubre
value,
la
this is
nueva forma de
bounded
ayudar a
over
proteger tu
by
hogar de los insectos con Pinol Limpiador Repelente. Limpiador para superficies que deja una barrera protectora que repele insectos hasta por 48 horas. Nuevo Pinol, limpiador repelente.
So if you will
Les
take the
presentamos
limit
Melimas,
only
la
for
nueva
this
suscripción
R,
de
then
Mercado
the
Libre.
maximum value of R
Con 12
can
meses
go
gratis de
for
música en Deezer.
capital R. So in absolute value, this is bounded ever by R over Wn minus 1 S over modulus of U depending on R comma W D of W, which clearly has limit 0 as R tends to 0. Yeah, because R is appearing outside here, so when R will tending to 0 because of the appearance of this term, this will be 0. So basically what we are doing, we are just putting a modulus here, then we are using the Schwarz inequality to take this restriction that R can have maximum value capital R and it will be bounded below by 0. So using the Schwarz inequality and this inequality, we will be arriving at this inequality. Now as soon as this capital R will tends to 0, this quantity will become 0. Use Schwarz inequality with this quantity. So we conclude u of 0 is equals to minus integration d z naught Laplacian of u dv minus integration over the closed surface delta d u del n g naught minus z naught del n u d of a. Now the definition of the green function. So Green's function in Rn with singularity. Now we are shifting the origin of the circle to any arbitrary origin. Earlier we were taking, if we are in 3 dimension, so we were taking this origin inside the domain, but now we are shifting the domain to anywhere in the space, and we are not sure whether the origin 0 0 0 coming inside of that domain or not. So what we are saying that we are considering the green function in the dimension Rn with singularity at x naught. So rather than taking it 0, we are taking this as x naught, y naught, z naught. And this green function is defined as when we have singularity at x naught, y naught, z naught rather than being singularity at origin of the domain, origin of the space. So here I was keeping R because we know that when we have center at 0, 0, then the equation of the ball is going to be modulus of x minus 0 is R. In the same way, if we have a center of that ball at x naught, then the equation of the ball is going to be modulus of x minus x naught equals to R. So it is up to you. If you want to write it here R, and if you want to write it here R, then it is fine. Only you have to mention that modulus of x minus x naught equals to R, because the equation of the ball or equation of the sphere or circle in n dimension, 3 dimension or 2 dimension is going to be the equation modulus of x minus x naught equals to R. So this, if you are writing in this form, then you don't need to change your Laplacian in the polar coordinates. However, if you are writing in this form, then you have to change your Laplacian in the polar coordinates, and then you have to proceed towards the solution of that Laplacian. At some point, if you guys feel that what I said that was not clear, then ask me for the repetition. So from the above definition for any bounded domain D in Rn, any C2 function, arbitrary C2 function. Mention that we are taking this arbitrary C function as second order derivative is continuous. Second order derivative is continuous. That's why because of this I am keeping this term. So from the above definition for any bounded domain in Rn and any C2 function U in the domain D and any point x naught belonging to D, that is basically the singularity, or you can say that it is a pole of the given green function. Pole. Do you guys understand between the pole, singularity, and what are the two more? Can anyone tell me? There is a pole and kind of singularity. Can anyone explain me the kind of singularity in the complex analysis?
Those are given by the Cauchy theorem, right?
Yeah. So one is the removable singularity. One is pole. Pole is not removable because the function is not defined at the pole.
Yes.
And it becomes unbounded. So this singularity is basically, you can say that pole at x naught, because it is not removable singularity. And there is one another type I don't remember at that moment because I have studied it in my master. So do you know what is the name of the third? Don't worry about that from here. So, and any point x not belonging to D, that is basically the pole of this green function. We have the representation formula. When it was 0, then we found this representation formula. When this 0 rather than being 0 is equals to pole of the green function. If x equals to x naught is the green pole of the green function, then it can be represented as u of x naught is equals to minus integration of d z x naught, the Laplacian of u, and then integration on the volume minus integration on the domain surface u del n g x naught minus g x naught del n u d of a. So this is the Green's representation of the solution of a Laplacian equation. So if you have a Laplacian equation del u equals to 0, then we are able to express the solution of this Laplacian equation in the term of the green function, and the green function has a singularity at a single point. It means the green function has a pole. In the case if the solution of Laplacian equation is going to have a discontinuity, then in that case we can define a function gx0 and can represent the solution in this form, because all the time the solution of the Laplacian equation may not be smooth, so that's why we need this representation. So what is the meaning of this expression physically? So physically, at least for n equals to 3, gx0 is the potential of a positive point charge located at x0. You may recall the electric field which we were discussing as an example in the last few classes. Recall the electric field equals minus the gradient of the potential in electrostatics. Where it is applicable, I am not giving the full description of that application because it is well written in the notes. I am just telling you, if you are going to proceed in the same way for the Poisson equation, this is the Poisson equation, then this representation will reduce to so basically what will happen, this Laplacian of u is nothing but f, and this gx is coming to be the same. And for the Poisson equation, if we are considering that the boundary condition is given in such a way that it is vanishing on the boundary, like del n u equals to 0 and del n x naught equals to 0, then this part will be 0 and we will be left with this part. So the same thing which is explained in your notes. So in the boundary condition, when the function vanishes on the boundary, in that case this will be this, and this is the representation for the Poisson equation. And you can also relate it with the delta function. Do you guys remember how I defined for the Heaviside function by taking the derivative? Okay, let me ask you one more question. Do you guys remember those calculations in which we were passing the derivative to the second function? No?
Can you repeat the question, please?
In the last few classes, we were talking about the Heaviside function, and then what we were doing, we took del 2u equals to 0, u and another function v, and u, either u or v were vanishing on the boundary. So we proved that v Laplacian of u dv over the domain D was going to be minus 1 to the power n minus 1 integration d, and then u Laplacian v dv, where either u or v are vanishing on the boundary. So we use the Green's identity to prove this identity. Basically the adjoint operator. Do you remember that adjoint operator? Have you forgotten?
Yeah.
Okay, so this thing is basically this thing is coming from that derivation. It was again a very long thing, so I was just writing it in a short way because for me only this representation formula was necessary. So I just give a basic description. If you want to derive this thing, so you can follow the book by Mac Owen, and he has given the derivation. He is using the same Heaviside and delta function and that adjoint operator to derive this thing. So I'm just skipping this part because only the most important thing was this representation. Because this thing, when either u or v are vanishing on the boundary and how the operator is passing to the second function, this thing we are going to use in the energy functional. That is also in the one of the topic. Now let's come to the topic eigenvalues of the Laplacian. This is going to be easier for you because it is just including the little bit calculation. So consider the equation. Consider the equation. In the domain omega and u equals to 0 on the boundary of the domain. So if this is the given problem, so can anyone tell me the trivial solution of this equation? What will be the trivial solution of this equation? Hmm?
A constant, right?
0. Because if you are taking a constant, it is not going to satisfy the boundary.
The boundary
We are
conditions.
taking omega is a bounded domain and this lambda is a number. For the time being, assume that lambda is a complex number because even in the case a real number can be expressed in this form, so it is also the subset of the complex number, so we can call the real number as the subset of the complex number. So that's why I am mentioning complex. It is a general form. So lambda is a number. Now we can see that the equation first always admits the trivial solution. Admits the trivial solution u equals to 0, but the value of lambda, but the values of lambda for which It admits a non-trivial solution, U are called the eigenvalues of the Laplacian in the domain omega, and the solution U is an eigenfunction associated to the eigenvalue lambda. Here you can see that we are taking this convention delta U equals to lambda of, rather than this convention we are using this one. So it is just for the sake of convenience, so that when we are going to calculate the eigenvalue of this equation, it will have a positive. So it is just for the sake of convenience. You don't need to worry about that, because this eigenvalue and eigenfunction problem will be very helpful when we have a Poisson equation. When we have a Poisson equation or an equation of the form delta U equals to A of U or a heat equation. So in that cases, this equation, this eigenvalue and eigenfunction method is going to be very helpful. More precisely, since we are taking the domain bounded, the boundary bounded, U equals to 0 on the boundary, it means the boundary condition is given on the dependent variable. The boundary condition is given on the dependent variable. So this is a Dirichlet problem, is not it? The boundary condition is given on the dependent variable, so it is a Dirichlet problem, and the boundary condition is again defined on the bounded boundary. So we can say that it is a Dirichlet eigenvalue problem. So more precisely, the solution to first should be called the Dirichlet eigenvalues and eigenfunction due to boundary condition involved herewith. In the same way, if the boundary condition will be involved on the derivative of this dependent variable, then what we call it?
Neumann.
Newman eigenvalue and eigenfunction problem. Yeah, that's fine. I understand the pronunciation. Sometimes mine can be bad and sometimes yours can be bad. Don't worry about that. Similarly, there are Newman eigenvalues and eigenfunctions, or other eigenvalues and
Positive.
eigenfunction
Positive.
depending on a choice of boundary condition. So in the same way, if we have the mixed boundary condition, so it will be the Robin eigenvalue and eigenfunction problem. Next, we are going to solve an example to understand the phenomena, how we are going to describe the eigenvalue and eigenfunction of the given n-dimensional problem. So to proceed towards the n-dimensional eigenvalues and eigenfunction problem, first we will take a look at a two-dimensional eigenvalue and eigenfunction problem.
But how do we know? How do we impose the conditions for the derivative of the function?
Sorry.
I didn't understand why the difference between the Dirichlet conditions and the Neumann conditions.
Are you confused about the boundary conditions?
Yes. How do you find the eigenvalues and the eigenvectors of the Neumann boundary conditions?
Yeah, that's we are going to discuss. So the thing is that if you have just think about this equation. So in this case, any solution which is going to satisfy this equation for a given lambda. So if you are able to find a solution u for given lambda, then we call that lambda is an eigenvalue and u as an eigenfunction. In that case, you will have
Yes,
some
yes.
arbitrary constant, is not it?
Oh, yes.
So to remove those arbitrary constants, we need some boundary condition. So when we are going to employ the boundary condition, that is this boundary condition, which is basically the boundary condition on the dependent variable. In that case, this solution is called the Dirichlet eigenvalue and Dirichlet eigenfunction. The same fashion.
Okay.
This is the easiest topic. Even in your sleep, you can understand this topic. Even if the solution is very easy, I think, from my point of view. The today class and the tomorrow class is going to be very easy. Like tomorrow, we are going to study the energy function. That is also very easy. So, firstly, we will see an example in which we are considering a two-dimensional Dirichlet problem, a two-dimensional Dirichlet eigenvalue problem. Let omega be the two-dimensional rectangle 0, a cross 0, b in the xy plane. Then the problem first becomes uxx plus uyy plus lambda of u equals to 0 inside the domain omega, and the boundary condition is 0 boundary condition. Well, I would like to ask you one question. What kind of, how you can distinguish that it is going to be an eigenvalue and eigenfunction problem? Just think about that and tell me. You have 2 to 3 minutes. Think about that. Why I'm calling it eigenvalue and eigenfunction problem.
I didn't understand your question. Can you repeat, please?
Yes, what I'm saying that this can be treated as a Poisson equation. It's not it, and this is a boundary condition, and we are going to solve. But in the previous classes, we did not mention that it is an eigenvalue and eigenfunction problem. What is the difference between the previous conditions and this condition for which we are calling it an eigenvalue and eigenfunction problem? Just think it is very easy. I think you know. Just have a look at this. And
Well, like firstly, we can. Well, I noticed that the operator, uh, when you when it acts on you, it's equal to a number times u, right? So that's an eigenvalue
more
for
precisely,
the operator. But
I would like to ask you if this u was not equals to zero, this u was not equals to zero on the boundary. Suppose this u was some function of x or y on the boundary. Then could you say that u equals to zero is going to be a solution, trivial solution, or u equals to constant is going to be a trivial solution?
No.
So that was the difference between the previous defined Poisson equation and this. Because when we talk about the eigenvalue and eigenfunction problem for a homogeneous equation, isn't it a homogeneous equation? Do you understand the meaning of the homogeneous?
yes, the function in the right hand side is equal to zero.
The functions, the equation where there is no source term. So we can write like this, isn't it? So this is a homogeneous equation. So when we talk about the solution of a homogeneous, just think about the ordinary differential equation, system of ordinary differential equation. I have some basic question. Talk about the system of ordinary differential equation A of x equals to 0, isn't it? So we say that x equals to 0 should be a solution of this different system of differential equation, is not it?
Yeah.
So in the same way, and then we proceed with the eigenvalue and then calculate the eigenfunction. So in the same way, since the given equation is your homogeneous partial differential equation of order 2. So the boundary condition which has a condition like u equals to 0, like a homogeneous boundary condition, u equals to 0 is going to be a homogeneous boundary condition. In that case, we are going to talk about the eigenvalue and eigenfunction problem. Suppose here your bounded domain was given like 0, comma a and 0 comma b. In some case it was not given like this. In some cases it was given a general boundary. So if we were defining u x comma 0 equals to z of x, then in that case u 0 comma 0 has to be 0. So g of 0 has to be 0. So this kind of condition will be given. So every time when we are going to tackle some kind of problem, so just analyze some basic things whether the given problem is homogeneous or not. If it is not homogeneous, then the non-homogeneous terms will be coming and the boundary condition can be anything. But when it is homogeneous, then we have to be careful with that. Again, we are going to use the method of separation of variable to solve this problem. So, use the method of separation of variable. And substitute the value of uxx and uyy in equation number 2. So we will be getting x double dash x y of y plus x x y double dash of y plus lambda x of x y is equals to 0. Now we are saying that the eigenvalue which we are assuming is going to be positive. So if lambda is positive, so it can be written as the sum of the square of two real numbers. Sum of the square of two real numbers. So write lambda equals to mu square plus mu square as per our assumption. Lambda is positive. So pass mu square with this. And mu square with this. Now, just divide it with the x and y. So you guys can see that this is an equation which has two separate functions, a function of x and function of y. So can we write the solution of the whole equation is going to be the summation of the solution of this and the summation of this? So the same theory which we are following in the previous classes to determine the solution of a Laplace equation with given a general boundary condition. Do you remember? Now the boundary condition is given u0 comma y is 0, ua comma y is 0, ux comma 0 is 0, ux comma b is 0. So when you will be employing that boundary condition u of x comma 0 is 0, it means x of x and y of 0 is equals to 0. This is general function, so y of 0 is going to be 0, which will be going here. In the same way, on the boundary b, it is going to be 0. Now, if we write it in the auxiliary form, auxiliary equation form, so the auxiliary equation is going to be m square mu square is equals to 0. So m equals to plus minus iota mu, and the solution is going to be x mx sine m pi x over a plus c2 cos n pi x over a. In both the cases, when you will be taking x0 equals to 0, so this will be 0 and c2 has to be 0. And when you are going to take xa equals to 0, again because of the, sorry, just wait. Sometimes I make a very blunder mistakes. So in the limit when x of 0 equals to 0, so this is 0 and sine 0 is 0, so 0 plus c2 cross 1, so c2 is going to be 0. So we are left with x of mu x equals to c1 sine mu of x. The second limit when you will be substituting x of a equals to 0, so it is going to give you 0 equals to c1 sine mu of a. Now c1 cannot be 0. Now c1 cannot be 0. So we have to take this sign of mu a equals to 0. And when sign is 0, when it is an integer multiple of pi. So the solution is going to be and the eigenvalue is going to be m equals to mx n pi over a. In the same way, you will be able to derive the solution of this equation, is not it? So mu n equals to n pi over b. Same way you can proceed and same calculation you can done for this, you can derive the solution. And then y of n by is equals to sine of n pi over b. Now with this equation we have the form of xm and we have the form of yn where m and n are integers, that is n comma n is varying from 1 comma 2 comma dot dot dot. Thus we obtain the solution of the equation second of the form. So if mu is this and nu is this, so what will be lambda? mu square plus nu square. Now say that lambda will be, sorry.
No, nothing.
So lambda, this yarn is very contagious. So I was taking this and then I passed to all of you.
What?
Yarn. What do you call?
Oh, yeah. Yeah.
It is contagious. So I was taking the yarn and then I passed to all of you. Sorry. So this is mu square plus nu square. What do you call in Spanish?
Bostezo.
Sorry?
Bostezo.
Can you
Bos-
say it?
B-O-C-C. C.
T?
No, not T. C.
C.
Set.
Oh, can you
Not
write it in the
C.
chat box? Can you write it in the chat box? Camilo is saying it is Z. Okay. I got it. B-O-C.
T. E.
E.
S.
Mm-hmm.
O. No. Oh no. I think it's switched. Now I don't know how to spell in Spanish.
Yeah, that's this. That's nice. I will let me write it. I will remember it because most of the time it happens to me, and I don't know how to call it in Spanish. Thank you.
Yeah, but the C and the S is switched.
Yeah, was this so?
Mhm.
So lambda mn is mu square plus nu square, and then it is going to be, when you are going to take the square, so pi square is going to come outside of that, and we are left with m square over a square plus n square over b square. So both integers are going to both integers are going to vary simultaneously. So when you will be taking one and then you will fix one and then you will vary the second. So according to one eigenvalue of this, there is going to be countable set of eigenvalue, is not it? When you will fix one m, then according to fix m, like suppose m equals to 2, then n is going to vary on the z. So according to m equals to 2, you are going to get a countable set of eigenvalue. Like suppose you fix m equals to 2, then lambda 2n, and this n is coming from the integer set of integers. So according to m equals to 2, we are going to get a countable set of eigenvalue, infinite, but that is countable. In the same way, suppose you fix n equals to something 1 to something, then this m is going to vary. Again, you are going to get a set of countable set of eigenvalue. It means the only one eigenvalue that will be a simple eigenvalue, lambda 1 comma 1. That is going to be a simple. Now I am stopping it here because this analysis is really very interesting and very easy. So we can start from here tomorrow and then we can proceed. For the time being, just write the solution. Since lambda is this, so the solution is going to be the product of this xm and yn. So u, the eigen function corresponding to this eigenvalue is going to be u m n x comma y is equals to sine of n pi x over 8 multiplied by sine of n pi y over v, and this is the eigenfunction corresponding to this eigenvalue. And when we are going to write the summation over all, like the solution of the given equation, in that case we will be taking the summation over m and summation over n. So it will be a double Fourier series. So this is your homework. Just go over the double Fourier sine series, and we can proceed beyond this point tomorrow. And tomorrow we are going to discuss how it can be generalized to n dimension. Okay. Do you guys have any question? Okay. See you tomorrow. Bye. Bye.
Bye.
Bye.